Hello, my name is Timothy Tian, and our group consists of me, Joanne Ling, Lim Chin Beng, and Ao Hui Ni. So this is our presentation for the Advanced Microprocessor Systems. And today I will demonstrate the spectrum analyzer implementation in software. So first of all, here is the code. It is written in Python, and I am running it in Jupyter. So firstly, I will do a quick run through of the code. So this code was obtained online and references will be provided at the end of this video. So first we import some modules, and the most important one over here is PyAudio. So this is the module that will read in the audio signal from the mic. And this one over here, scipy.ffmpeg, this is the library that will allow us to use the built-in FFT command to perform the fast Fourier transform on the input signal. Next, we have this one over here, matplotlib.tk. So this will allow us to show the spectrum in a separate window instead of the same window. So now we first define some constants. So these are the samples per frame, the audio format, a single channel for the microphone, and also the number of samples per second, which is 44.1 kilohertz over here, double the frequency of the usual signals which can be heard by humans. So next, this command will plot the figure. So we have figure, and this is the first plot and the second plot, x1 and x2. So x1 will represent the waveform in the analog form, and ax2 will be the waveform after FFT is conducted on it. So ax2 will represent the waveform in our frequency domain, which is the spectrum analyzer. So first, we have the object P. This is where we read in our audio, and we open object P and read it into object stream. So stream will contain the data of our audio. The next, we have the variable for our x-axis plots. So x is the variable for our first plot, and xf is the variable for our second plot. So our first plot is the waveform in the analog form, in the analog signal, and xf is the x variable for our waveform in the frequency domain after FFT. Then next, we have these two line objects. So these two will be constantly updated in a while loop later on, and this allows us to show the result in real time. So this is where we plot the x variable. So next, we have some definitions for the waveform axis, such as the title, the x label, y label, the y and x limits of the graph, and so on. So this is done for ax1, the first plot, and ax2, the second plot. So next, we have the while loop over here. So this is where the data will be constantly updated to present the graph in real time. So we read in the stream object into data, and we post-process it to data integer, and finally to data MP. So this is where the data MP will be fed into the line object to create the plot. So this will be the line object of our first plot. And we also take data integer and run FFT on it. And this is fed into YF. So this is where we will plot the second graph. So using line FFT, the object earlier on, and using YF, which is the data after FFT is applied on it. So this will give us the graph of the waveform in frequency domain, which is the spectrum analyzer. So finally, we will draw up the figures with these few commands below. So now I will demonstrate the waveforms. I will run the cell, and these are the two waveforms that are generated. So as you can see, the top graph represents the signal in the analog form in the time domain, and the bottom graph shows the waveform in the frequency domain. So as you can see, while I am speaking, the waveform is already being generated. So right now I will play a tone from a tone generator. So this is a tone of 440 Hz, and you'll be able to see the signal being formed. So as you can see in the top graph, a sine wave was generated, and in the bottom graph, a peak was generated at that frequency. So now I will play another two tones, one of a higher frequency and one of a lower frequency, and you can see the difference in the waveforms being generated. So here is the high frequency signal of 590 Hz. And also the signal of a lower waveform. This is 300 Hz. So those are the waveforms being generated in the analog form, and also after it has undergone fast Fourier transform, which is after the signal is converted into the frequency domain. So finally, here is the reference for the code. This is the page where the source code is obtained from. And I will include the link of this source code in the description box below. And that concludes the presentation. Thank you.